Hello everybody, this is Avantik here. Today we'll be discussing about model selection and evaluation. This is a very important module if you're a data scientist because you will be continuously working towards fine-tuning your model, finding the better model. So this is all about that. The topics that we'll be discussing over here are cross-validation, hyperparameter tuning, model evaluation, model persistence, validation curves, and learning curves. Let's start with cross-validation. The first topic of this module, cross-validation. Let's first understand what are simple models, what are complex models, though we have used them for a while now. Simple models in terms of decision trees would be something where you have configured with limited height. Okay, say your maximum height of decision tree that you have configured as a hyperparameter is say 5, and the complex version would be say 15. Okay, these are relatively simple and relatively complex. In terms of linear regression, say simple linear regression would be a simple model, or and a polynomial linear regression would be a complex model. Okay, so if you increase the degree of polynomial, you will get much more complex model here. And the thing that we have to understand, if you increase the model complexity, as you can see here, the variance increases. What it means is the behavior of the model is different for training data and validation data. The gap between them is more compared to the model which is less complex. A less complex model will have less variance. That means be it training data or unknown data, it will not show much of a difference in the accuracy, but the accuracy will be less. So what it means, the variance is less but bias is more. Okay, and similarly for complex model, the bias is less but variance is more. What we intend to do is intend to find the best trade-off at which there is an optimal bias and optimal variance. To arrive to this conclusion that which model has optimal bias and conclusion, which model has optimal bias and variance, there are a lot of experiments to be done. Okay, and cross validation allows you to do that with simplicity and generalizability. Let's understand. We have a simple decision tree here, okay, that we'll use, and we are loading MNIST data, load digits. Okay, and this is how 3 would represent, right? We're trying to print 13th data, and this is how it is 3. Okay, this 3, right? This is the data, this is the target. Let's first create a complex model. Okay, decision tree and maximum depth that you are configuring here is 10. You're not trying to split the data into 2 parts, the training data and the validation data. This is the first technique using train test split. We have used it before. This is the first simplest technique. It randomly divides the data into 70-30 ratio. Of course, you can configure it further. Okay, after that, you're training with the train part of the data. And once you are done with that, you got a train model, and using this train model you are finding the score with unknown data, that is test X and test Y, and you are also finding the score with training data, and you can see the difference between them. It's around 13%. So the accuracy of the model for known data and unknown data is quite high. This is what is high variance. So a model with depth 10 is showing quite high variance. Now if we decrease the depth, right, we are decreasing depth of the same model to 7, and we can see the variance decreasing, right? Of course, the bias also gets increased and variance decreased. That means accuracy falls down, but it is the gap between the training data accuracy and testing data accuracy is reduced here. The next technique to do this is cross validation score. Okay. So how it works with cross validation score is, by default it splits the data into 5 parts. 4 parts it will use for training, and the 5th part it will use for validation, and it will repeat this step 5 times. Okay, and when you do scores.mean, it will find, that's what we have done, cross validation score. This is the model, this is the training data, this is the training target. We're using all the data over here, and we can see using this process it got an accuracy of 74%. Okay, and it is doing a mean of it. That 5 results, it's actually doing a mean of it. The next way to do this is using cross validate function. Now we'll, after cross val score, we'll see cross validate, which is much more flexible and it provides a hell lot of information. Okay, so here using not only the accuracy technique, which is by default for classification, you want to get precision macro, you want to get recall macro, right? These are different errors. We'll understand going down the line what this means, but these are like different type of errors. You want to get all those, and how much time did it take to train the model and everything around it. You use cross validate. So this is much more superior API, which gives a lot of information. The third technique is stratification. Okay. Now the data actually may be imbalanced. That means there is lesser data of one class and more data of another class. Okay. So what we intend to do is we want to split the data into train and test, but at the same time we want to maintain the composition of the data. Okay, so that is where stratification comes into picture. It divides the train and test in the same ratio as the actual data. Okay, so that's what we are doing here. We are generating some 18 rows of data over here, and stratified k-fold we are configuring number of splits, and once we configure the number of splits, it's returning 3 data. This first data is your training data, this is first data, this is second data, this is third data, 3 data. So it's returning 3 subsets, three composition of it, and it tries to maintain the same ratio as the actual data in the train and test part. So this was like different methods of cross validation. Okay, and make sure before we pitch your model to your customer, consumer, or for competitions, you use cross validation to find a generalized behavior of the model. After this, we'll be getting into hyperparameter tuning. Stay tuned. Let's understand hyperparameter tuning. We all understand that there are 2 types of models. One is parametric and non-parametric, and you need to configure parametric models with a lot of hyperparameters, right? So that you get the best complexion of the model for your deployment scenarios, right? And finding the best hyperparameters is known as hyperparameter tuning, and there are 2 major APIs which we'll be using for that. One is grid search, one is randomized search. Okay, so what we do over here, and we'll try to understand this using decision tree and the same MNIST data. So what we have here is we have split using the simple API of train test split. We have split the data into 2 parts: training data and testing data. Train X, test X, train Y, test Y. Okay, this is your feature data, this is your target data. This is the model decision tree classifier. As you can see here, dt is equal to decision tree classifier, and now we need to find out what is the best optimal height of the tree. Okay, so what we have done for that, we have a dictionary which is configured over here. Of course, you can configure it separately, but there is a dictionary that we are configuring, and this dictionary consists of, this is the hyperparameter, this is the argument in decision tree max depth, and we are configuring with all the possible values between 10 and 30 separated by 5. Okay, this is your grid search, and we have mentioned cross validation is equal to 5. What it means it will, before it tells you the score, it will divide the data into 5 parts. 4 parts it will use for training, 1 part for validation, and it will do this 5 times, and it will mean it out and give the results to you. Okay, that's what it is. It is grid search, and once you have configured it, trying to train the model, you're training it using fit. Okay, and you want to find out what are the best hyperparameter in this range. If you do grid search dot params, it's returning that 15 is the best height of the tree, so that it gives good results. Best score was 78 using same decision tree. Okay, and you want to find the best model which was trained using max depth is equal to 15. This is what you get, best estimator. It will return you the model, and this is what you should be using. This was grid search. The next technique is randomized search. So grid search is a sequential technique. It will try for all the data that you have configured. Randomized, randomly tries various things. Of course, its accuracy is not as good as grid search, but performs quite well, because grid search has a tremendous work to be done. It has to brute forcefully look for all the data, right? Randomized, whereas tries to fine tune or minimize the number of experiments it will do, and still get a good result. Let's see that in this experiment. So this is the parameter. So as you can see, there are a lot of hyperparameters to be configured. Okay, and you have this rand int. Okay, rand int is present inside SciPy stats. What this does is this, whatever value you have given in 1 to 11, it tries to randomly generate numbers in this range. That's all it does. Okay, so we have max features, we have min, sample, split. All, so 1 to 11 is the range and 2 to 11 is the range, and rest of the stuff is configured over here. Okay, so when you use, you have random forest classifier where the number of estimates is 20, and this is the parameters we are passing it over here. This guy random search took 7.48 seconds. As you can see here, before doing the fit, you are doing a start time. Start is equal to time, and after the fit is done, you calculate the time again, and you're finding the difference. This tells you how much time did it take to execute the step. Okay, and as you can see here, this guy typically took around 7.48 seconds, and you got an accuracy of 92.8. The same thing you try to achieve using grid search, and you see that you got 30, it took 30 seconds, and the best score was 93.4. Of course, we don't see a huge difference between them, but in terms of time, we see a huge difference. So randomized search will give you quickly the one of the best hyperparameters, and but may not be the best answer, best model. Okay, so you might be a little close to the best answer, but it gives you quickly the results. I definitely encourage everybody to try random search so that you can get close where the answers are, then maybe fine tune it further with grid search. Let's get to the next topic of the module, model evaluation. Now, there are a lot of techniques by which you can find out what is the performance, how is your model performing, and all that. But depending on the problem that you're trying to solve, you might use different techniques. Let's understand. For example, if you talk about predicting whether the patient is suffering from cancer or not, if you falsely classify a patient not suffering from cancer as patient suffering from cancer, you might do a couple of tests, but after that you might confirm, okay, the patient is safe. What happens if you do the other way around? A patient suffering from cancer, you're predicting as fine. The patient will never undergo the test, and maybe by the time you're looking up the patient for the second time, it might be a little too late. Okay, so misclassification is fine, but you have to understand which one you are giving more gravity. If a normal mail goes to your junk mail folder, that's much more severe than a junk mail coming to a normal mail folder. So you have to understand based on what type of model you are looking for, which is the type of error you are going to let go. That is where your understanding of model evaluation techniques comes into picture. So you have different matrices for that, and scikit-learn is very rich in terms of that. Let's first create a model and get some prediction out of it. So as we have used throughout, splitting the data into train and test, training the model, and we are using the score function, which uses the default function. Okay, so as you can see, for random forest, we are getting an accuracy of 96.8. Okay, so this is the default function. So if you do rf.score, it internally uses accuracy function, and it calculates that. So the next technique is using cross-validation score. So cross-validation score, this is the model, this is the data, this is the number of splits that you're allowing, and it returns you, as you may have mentioned, CV is equal to 5. It's returning you 5 accuracy based on how much divisions you made. Okay, so 5, 4 training, 1 validation. You did this 5 times, and this is the accuracy that you got. So your overall accuracy would be mean of this. Now we'll understand the detailed technique using matrices, which provides further more techniques of identifying how good is your model. Okay, let's use breast cancer data. This is a decision tree that we're using, splitting the data into train and test. Okay, then you're fitting the model, gt.fit. Post fitting the model, you are actually passing the training data over here, and this is the prediction. So let's now understand various matrices for getting into details here. So let's see what we have. The first one is accuracy score. Accuracy score is nothing but how much correct classification you did by total number of observation. So this is the thing that gets used by default. Okay, when you use estimator dot score function. Okay, followed by that you have the next method, which is known as confusion matrix, which provides little more details about misclassification. As you can see here, there are 4 types of information. One is true positive, true negative. True positive means the data belong to class 1 and you're predicting it as the data belongs to class 1. True negative is data belongs to class 0 and you're predicting it it belongs to class 0. Then you have false positive, actual class is 0 and the prediction is 1. You have false negative, actual class is 1 and you're predicting as 0. Okay, so if you have, I think the first two are very simple. If the patient is suffering from cancer, you're predicting it that the patient is suffering from cancer. This next guy is 0, the patient is not suffering from cancer and you're predicting that patient is not suffering from cancer. The false positive is that the patient is not suffering from cancer and you're predicting that patient is suffering from cancer. The false negative is patient is suffering from cancer and you're predicting that he's not suffering from cancer. Okay, so just to map it. So when you do confusion matrix for this data, it prompts this. So as you can see, this is correct. The diagonal information is correctly classified, and this way it is right. It means actual no, and you're predicting as classified. This is actual yes, and you're misclassifying it to no. Okay, so this is what is confusion matrix. It will give you clarity around what is the misclassification information, and based on that you can take a call if your model is suited for this particular application. Followed by that, you have precision score. Precision score, what briefly it means is you have ability of a classifier not to label a positive if the sample is negative. Okay, so for example, we don't want to mark a non-spam mail as spam. Okay, because you'll never end up, maybe that's job offer, right? You'll never end up reading that mail. So for that, those models, you have to consider precision score. Then you have the other way, which is this was example that I used. If it's not okay to miss a cancer patient without further analysis. That means a patient is suffering from cancer and you're predicting him not to be suffering from cancer, right? So that error is not okay. So in that case, you would prefer an algorithm which shows better recall score, and this should be your criteria for choosing the algorithm. And if you want a balanced version of both precision and recall, you have this F1 score, which have a balanced version, weighted average of precision and recall, right? Let's get into the regression errors. Okay, so what we have here is housing data, California housing, right? And this is the model that we have created from training this data to the model, right? And this is the prediction. So there are 3 types of error. One is mean squared error. Okay, that's basically sum of square of difference between the actual value and the predicted value. Followed by that, you have mean absolute error. Okay, that's basically the difference between the mode of the difference between the predicted value and the actual value. And followed by that, you have R score, right? R score, R2 score is what it does. It tries to bring the above 2 error is not limited in the range of 0 and 1. So it will be some values. As you can see, it's 0.5. Okay, so it can be 10, 100, anything. The R2 score, it will actually bring the data in the scale of 0 to 1. Okay, so remember, R2 score can also be negative. That means the prediction is totally haywire, right? So this also tells you basically how your model is. But remember, it will be in the scale of 0 and 1. How it is a technique by which you can say how goodness of fit is the regression model. So this is another way. So 3 popular ways for regression. And for clustering, okay, you can refer to this after you have finished clustering modules. But in terms of clustering, you have to find out how good is your cluster. So assume that you have used, you have 8 to 10 different techniques of clustering, and you want to see which clustering method is suiting your data. So you have various techniques over there. And formally, there are 2 types of clustering technique. One is your supervised, other is unsupervised. Okay, and supervised techniques of clustering, measurement are of 2 types: completeness score and homogeneity score. Unsupervised Silhouette score and Kalinski-Harbert score. Right. Let's now understand what is completeness score. Okay, the first one is completeness score. What this tells you is, given a cluster, say you have the data and the data has class information. Okay, now if there is a cluster which contains all the data of that particular class, of course the cluster can contain multiple such classes, right? That is known as completeness score. That means how complete is a class of data in a cluster. Let's understand this with an example. Say this is the true label, okay, 10 10 11 11, and if you're trying to do trying to map this 10 10 in one cluster and 11 11 in another cluster, this will return 100% accuracy, 100%, right? One. And similarly here you can see 1 11 22 22 11, and you're saying 11 22 and 11 belongs to cluster 1 and 22 belongs to cluster, this 22 belongs to cluster 0, the accuracy is less. Okay, so again here, so 10 10 11 11, all this belongs to same cluster 0. So that was the rule here, right? So completeness means how much class of the class data belongs to one cluster. As you can see, this 10 10 belongs to cluster 0, 11 11 belongs to cluster. There is no other cluster over here, so the accuracy is 100 here. This is completeness score. So if we want to have a situation where all the class data belongs to one cluster, we will want to check completeness score. The next technique is homogeneity score. Homogeneity score, right? So what this means is if all its cluster element contains data points which belongs to the same class, of course now it can be spread, right? For example, again 0 0 0 and 0 belongs to cluster 1, 1 and 1 belongs to cluster 0. So this is a perfect case. Let's understand this situation. 0 0 0 belongs to cluster 0, 1 belongs to cluster 1, this 0 belongs to cluster 0, cluster 1, this one belongs to cluster 2, this one belongs to cluster 3. This also shows around 100% accuracy. That's because each cluster has only one type of element. That is what homogeneity is. How homogeneous is a cluster. Of course, same class data can be spread across multiple clusters. Then the other two techniques are you're suited for unsupervised. That means you don't have the target information over here. So as you can see here, Silhouette score. So many times we need, when you are doing k-means or other clustering technique, we need to find optimal number of clusters. So we need a mechanism to tell that, you know, what is the, should we be dividing this data into 2 cluster or 4 cluster or 3 cluster? What should be? So this is where your Silhouette score comes into picture. So let's say this is the data that we have created, and we are trying with different values of possible range of clusters. As you can see, these are possible ranges, and when you are fitting the model and score, and then we are calculating Silhouette score for X and the labels, right? Silhouette score. So this is prediction is the this predict function. It's returning the cluster to which it belongs. So we're trying with cluster 2, cluster 3, cluster 4, cluster 5, cluster 6, and you can see here the accuracy or the score is pretty high for cluster 2. So that is what becomes you know, the best possible option to divide this data. So it uses the intra-cluster distance and this cluster and this cluster distance. The function of that you can refer to this, you know, by this math over here. Okay, so B is the distance between a sample and the nearest cluster that the sample is not part of. Okay, so B minus A is the intercluster distance divided by max of A comma B. So this is what it is. So basically you're trying to find out what is the optimal number of clusters over here. Okay, the other technique is Kalinski-Harawas score. So what this tells you is the ratio, you know, it's defined as a ratio between cluster dispersion. Okay, how far within the cluster data is versus the cluster from other cluster is. Okay, so of course this is not in the scale of 0 to 1, and here also we'll see you know, the score, lesser the score the better it is, right? So 2. As of now, we have seen different ways of, you know, measuring the model. These are known as model matrices. Of course, this is not all. There are a few other things that you can give it a shot, but more or less, this will give you a good idea how to choose the model. Welcome to the next part of it, where we'll discussing about model persistence. You know, you created a model, awesome, great. You fine tune it, awesome. What's the next thing? You need to ship this model to the customer, right? You need to ship this model to your validation team where they will be extensively testing your model and getting confidence over it, right? So when you want to do so, you want to ship your model. You don't want to ship your code, you want to ship your model. That is where techniques like joblib and pickle comes into picture. It is the model that you have created earlier. You do pickle.dumps dt, it will pickle the model, that means serialize the data. That basically it will be in string format. And once you can do pickle.loads s, right, it is reloading the data, but of course it is not shareable and all. If you want to share the model across different computers, different network, right, you would use an extended version of pickle, that is a joblib, which is designed for this. It is present in sklearn.externals joblib, and you do joblib.dump. This is the model name, this is the file name. So it actually converts the model into a file, and you can imagine what you can do after that. You can ship it to the customer, and once anybody get the file, he or she just does joblib.load and the file name. This is the model that has returned, right? Okay, so after this you can use fit, fit, predict, whatever you want, you can do that. And remember, if you use fit, it will forget the previous training. If you do predict, of course it will use the trained model and proceed further. If the model supports partial fit, it will train on top of it. This was about model persistence, right? So that you can share your model for production, you can ship your model, you can transfer your model, right? Next, we'll be getting into validation curves. So validation curves. Okay, so what we want to do, we want to see how our model is shaping up as we change certain values in the hyperparameter. We want to record all these things and see how the model is getting improved, or it's not improving. We want to understand all those things, right? So sklearn.model selection import validation curve. Param range is equal to np range 1 comma 50 comma 2. What this is returning is 2 separated 1 to 50. It's returning all the data over here. Then you have train score and test score, and you have the function validation curve. Okay, this is the model it's taking. This is the training data. This is the target data. This is the parameter that we are interested in, say an estimators, right? And this is the range of values for the estimator 1, 3, 5, 7, right? Followed by that, we have this CV is equal to 3. This is the cross validation. This is how much time you will be splitting the data, and whatever accuracy you claim. This is the split part, and the accuracy that you are using, the matrices that you're using, you are mentioning accuracy over here. N jobs is equal to -1. Keep it in mind when you are using grid search or randomized search. N jobs is equal to -1 means you're making use of all of the cores of the system, right? So it relatedly optimizes. Once you have created the validation curve, when you run the model, right? So it will be storing all the values in the train score and test scores, right? And that's what you are doing over here. You're calculating mean across all the all 3 subsets, right? And you're plotting it, right? So this is your training data. This is your training score. This is your cross validation for the unknown data. As you can see, there is some difference. That means there is a variance, right? And this is the only hyperparameter that you are using here is number of trees, number of n estimators, right? So this is with increasing number of trees, you can see, it's pretty much getting balanced over here. So no need to increase the number of trees beyond 20, right? That's the impression that you get here. And you can see training part has pretty much labeled at 10, 8 to 10 trees. The next topic that we'll be discussing is learning curves. We really want to know how much data is really required to train the model. What was the optimal data size? That's okay. So if you really increase the data, is there a possibility of your model improving any further? So that's what you want to know, and that's what learning curves tells us. So this is the data, this is cross validation, and this is the training sample size. Okay, 0.01. Okay, 50 different sizes of training data, 0.01 to 1, right? This is the range, and you're generating 50 different sizes. So let's see what we get. And this is NP mean, and this is doing, remember, the cross validation is 10. It will divide the data into 10 parts, and it's just calculating mean of each row. Okay, so when you do so, you can see here, this is the 100% accuracy, and you can see with increasing data, your model is getting pretty much balanced, something around 1200 iterations, 1200 data. maybe 1200 to for last 400 data didn't add a lot of things over here. So you might reduce it. And if you still see there's a possibility of picking up, you add more and more data over here, right? Okay, so that's pretty much all. You try it out, all the stuffs. These are like quick things that you do to understand how good is your model performing. That's all from this module. Thank you guys. See you in the next video.